Welcome back. In our last segment, we learned how to manage our application using deployment, which gives us the self-healing and controlled rollout. But what happened when the traffic to our application suddenly increased? We need to handle that load, and that's where one of Kubernetes' most powerful feature comes in, scalability. Today, we are going to explore the different ways to scale our workload. We'll start with the most direct method, manual scaling. And then we move to the intelligent automated approach using the Horizontal Pod Autoscaler. Manual scaling is exactly what it sounds like. We explicitly tell Kubernetes how many replicas of our application we want to run. It's the most straightforward way to adjust our application capacity. Right now, if we check app mem cache deployment, we should have 4 replicas. So let me create the app mem cached. The replicas created for the deployment. So let's get the pods to see, are they running? Yeah, 4 of the pods are running. Let's say that we are anticipating low traffic for the weekend and we want to scale it down to 3 replicas. We can use the kubectl scale command. So we scale down the deployment to replica 3. So in this way, if I check the pods, you can see one of the pods got removed and we only have 3 pods running. Behind the scene, the deployment controller sees that desired state now is 3, but its current state is 4. Immediately start removing one pod to reconcile the difference. If we check our pod again, we'll see that once the old one is got removed. It's that simple. We just manually decrease our application capacity. So about the stateful set, this same command also worked for other workload types like stateful set. Stateful sets are used to stateful set application like database, where each pod needs unique stable identity. There is no command line for creating stateful sets, so we have to use declarative YAML file for creating the stateful set, unlike the deployment, which we can use the kubectl command. So I'm going to create a YAML file named redis.yaml. And then as you can see, the kind is a stateful set. The name is Redis. The replicas are 3. And the match label is Redis and the Redis and then container. So it's very similar to deployment, but there is a major difference. Let me apply this change. Okay, apply -f redis.yaml. So now we should have pods of Redis running, but the major difference is these numbers. Unlike the interchangeable pod in deployment, stateful set pods are named with a predictable original index, like Redis 0, Redis 1, Redis 2. Each one gets its own persistent storage that follow it, even if it gets rescheduled. So right now I don't have any storage, or we'll talk about the storage later and stateful set. That's the most important usage of a stateful set in future. But imagine that we will remove this pod, Redis 0. When what we expect is that when the pod comes back attached to the same storage that it was using. So we are not losing any data or in any inconsistency in the cluster. That's the whole point of using stateful set. So now I want to increase the replicas from 3 to 4. So right now we have 3 Redis nodes. I increase it to the 4 pods. So if you can see that we can now we have 0, 1, 2, and 3. So let's scale it down. Let's scale it to 1 pod. We can see that they are terminating and only Redis 0 is remain. This is the beauty of scaling up and down manually. So manual scaling is great, but it has a major drawback. It's reactive. It required a human to monitor application load and guess when scale up or down. If you are too slow, your users suffer. If you get forgot to scale down after the traffic spike, you're wasting money on idle resources. Especially this is important in cloud environment when you can spend thousands of dollars without knowing that you're spending your money on something that's unnecessary. So the solution to automate this process for this, Kubernetes provide the HPA or Horizontal Pod Autoscaler. The HPA acts as a smart thermostat for your application. You give it a target metric to maintain. For example, keep the average CPU utilization across all pods like 80%. And the HPA controller does the rest. It constantly watches the metrics, automatically adjusts the number of replicas up or down to meet your target. So the horizontal pod autoscaler sounds amazing. It watches metrics like CPU and memory and makes a scaling decision for us. But this is lead to a critical question. Where does the HPA actually gets the data from? The answer is a crucial add-on called a metric server. Think of metric server as a central nervous system for resources metrics in your cluster. It's just simple but vital. It collects resources usage data like current CPU and memory consumption from the kubelet on every single node. It aggregates this data to expose it through the special Kubernetes API called metrics.ks.io. It's designed to be lightweight in memory source for the current state of resources usage. Its main job to serve this data to other Kubernetes components that it needs, like HPA and command line kubectl top. Without the metric service, the HPA has no data source. It would be flying blind and completely unable to function. When you set up a cluster with kubeadm, you get a lean, comfortant Kubernetes installation, but it doesn't include add-ons like a metric server by default. The good news is that installing is incredibly easy. To enable the metric server on kubeadm cluster, we just need to apply a single YAML manifest to provide the official Kubernetes project. Okay, now I'm applying this change, and now if I'm doing the kubectl top node, we should see that the metric server is enabled and we have the information here. If you get back resources usage data like this, your metric server is running correctly and the HPA now has the data feed it needs. Before we create an HPA, there is one absolutely critical prerequisite. For HPA to calculate the CPU utilization as a percentage, it needs to know what 100% is. It gets from the baseline from resource requests you set on the containers on your deployment pod template. If you don't set the resource request CPU, the HPA won't work and it will show you an unknown state. In the next lesson, we will talk more about this request and limit. Okay, let me get the HPA now. As you can see here, the target is unknown. That's because the deployment doesn't have any requests. Let me just define the autoscale for our deployment and set it like 80%. So if we get the HPA for this app memcache deployment, we can see that the target CPU is unknown and then the target is 80%. So to set the information resources coda, we need to edit the deployment. Let's edit the deployment. Okay, get deploy, and let's edit this one. Deploy app memcache. Okay, here on the resources section of the spec, you can see that it's empty. So now we are going to add information here. So as you can see, the request is 15 millicore, 50 millicore. So HPA need this baseline. So it means that these pods are requesting from the scheduler 50 millicore. This doesn't mean that this pod is limited to only use the 50 millicore CPU, but it means that scheduler knows that this pod is using 50 millicore by default. This is crucial part for resource management in Kubernetes. With that in place, let's create our own HPA, which I created. Like CPU percent is 80% and minimum pod is 3 and maximum is 5. Now let's inspect the HPA we just created with kubectl get HPA. Kubectl get HPA. So now you can see that current usage is 2%. So then the pod is not using lots of CPU at the moment. So we can see that usage by ktop pods. And as you can see, right now it uses 1 millicore. And the memory is 1 milli. You can see that our HPA is targeting deployment with our min max defined. If we set application under heavy load, the CPU usage would climb. As soon as the average utilization cross our 80% target, the HPA would automatically scale the deployment up to the 5 replica. Once the traffic subsidized, it would scale it back down to the minimum of 3, saving us resources. Testing the HPA with a live load test. We have been now created the Horizontal Pod Autoscaler, and you can see that it's targeting our app cache deployment. But right now it's idle because there is no significant load on our application. Let's change that. We are going to generate some real traffic to see our HPA spring into action. Before our benchmark tool can send traffic to our memcached pod, it needs a stable network endpoint to connect to. Pods are ephemeral. They can be replaced, and their IP address will change. The solution in a Kubernetes service. I'm going to create a cluster IP service. This type of service provides stable internal IP address that's only reachable from inside of the cluster, which is perfect for our test. We'll do a deep dive into all different service types in our networking lesson later on. For now, just remember that the service gives us a single reliable address to access our group of pods. I'll use a quick imperative command to create it. Okay, kubectl expose deployment, app memcache, and type is cluster IP, and the port is 11211. And the target is also 11211, and the name is app memcached. Okay, now if I get the services, you can see that the cluster IP is 10.11.111.111.2, and the name is app memcached. So the next step we'll create a separate pod that just run our benchmark tool. We'll use a standard performance testing image from Redis lab called memtier benchmark. So now I'm running this pod, the container creating, it's under happening. So we are using a little trick here by telling our container to run a sleep infinity command. We will keep the pod alive infinitely so we can get a shell inside to run it in our test. Now let's execute a shell inside of our new benchmark tool, like kubectl exec -it memcache. So right now I'm inside of the pod, and To demonstrate the load test, I'll split my terminal into two terminal. I'll connect to Node again. Then I'll use export to export my kubeconfig and set my alias. Okay, now everything is ready to do the actual benchmark. To watch all the changes, I'm using the Linux command watch, which is running this command every 1 second and print it on the terminal. So right now I'm getting the HPA. You can see that the CPU usage is 2% and these 3 pods are running. So if we face any like increase in traffic, then the HPA should create or enroll new pods for us. Let's run the benchmark and see what's happened next. Okay, this is exciting part. I'm going to split my terminal so you can see the two things at once. And this is the second terminal. So I'm going to watch and you can see that HPA is currently reporting low CPU target. And we have 3 replicas. And now you can see increase in CPU, which is more than 80%, and 2 new pods created. So yeah, and there it is. The HPA has reacted. Look at the replicas count. Just jumped from 3 to 5. And the bottom, you can see that new pod is a container creating a state and running. Though the HPA doesn't yet. The average CPU is still too high, so it's scaling up again. The replicas can't just hit 5, which is maximum we allowed. That HPA has perfectly scaled our application out of the handle for this massive sudden spike in traffic. Okay, I'll cancel this load test. So the benchmark is complete. Now the CPU load will start to drop across 5 pods. After default cooldown period of 5 minutes, the HPA will determine these extra replicas are no longer needed. It will then begin to scale down deployment back down to minimum 3, automatically saving us resources. This is power of autoscaling in action. Completely automated, intelligent responses to real-time application load. So the latest version of the HPA API, Autoscaling 2, allows for even more sophisticated rules. You can configure it to scale based on multiple metrics at once. It's like CPU and memory. So we can use like utilization and memory. This configuration tells the HPA to scale up the CPU utilization exceeding 80% or like memory for 50 more megabyte of memory. Finally, it's important to know the difference between horizontal and vertical scaling. Horizontal scaling, which is what HPA does, change the number of the pods. It's scaled out by adding more replicas. Vertical scaling, managed by Vertical Pod Autoscaler or VPA, change the resources allocated to pod itself. It scale up by giving existing pod more CPU or memory. While the HPA is more common for handling traffic spikes, the VPA is excellent tool for understanding your application resources need. You can run it by recommended mode and then analyze your pod usage over time until the optional request and limit. You should set your deployment. So conclusion, manual scaling like kubectl scale give you direct and simple control. The horizontal pod autoscaler automatically scale the number of replicas out and then based on real-time metrics makes it perfect for handling variable load. And the vertical pod autoscaler helps right-size your pod by adjusting their CPU and memory allocation. By combining these tools, you can build applications that not only resilient, but also incredibly efficient, using just right amount of resources to meet user demand. Thank you for watching. I'll see you in next topic.